and we look forward to gaining valuable insights from your expertise. Now, I invite Mr. Shoni Gregan, Assistant Professor, Department of Electrical and Electronics Engineering, to formally introduce our resource person to the gathering. Sir, please.
Good evening, all. A warm welcome for the day 4 of FDP on advanced and application of smart materials in environment and technologies, conducted by the Department of Science and Humanities of Marthandam College of Engineering and Technology. I am deeply honored to introduce today's resource person for session 1 and 2, Dr. K. Vinod, Scientific Officer, Indira Gandhi Center for Academic Research, IGCAR, Kalpakkam, Tamil Nadu. He did his PhD in NIIST, India, under the area of low temperature condensed matter, superconductivity, magnetism, and magnetocaloric effect in 2010. With more than 20 years of experience, he has published more than 60 journals and a patent as well. With immense pleasure, I would like to invite Scientific Officer Dr. K. Vinod to share his knowledge on the topic of material magnetism. Welcome, sir. Now I hand over the session to the resource person. Over to you, sir.
Thank you, sir, for your introducing the resource person to the gathering. Now I hand over the session to our esteemed resource person, Dr. K. Vinod. Welcome you, sir.
Hello. Connection. Now I connected with the desktop. My audio. Whether is it audio also? Is it screen is there? Audio not there.
Yes, sir.
Okay.
You are audible, sir.
Sir, now it's audible, sir.
Not a headphone. I have this. What is called the webcam only. Webcam with a microphone and it is still a microphone also. It is, I don't know. Otherwise, mobile I will take. But through mobile also we can do now. Okay, I think then mobile may be more confident. Okay, okay. Okay, so from this I have to sign out. I have to come out from this one. Okay. 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 Actually, I am not that much confident. Okay.
Participants, please wait for a few minutes.
Since the system is not working properly at this, so travel is shown. So all the participants requested to kindly wait for a few minutes.
Hello? Huh? But my audio is there. My okay. If audio is you call back.
Yes, sir. Yes, sir. It is audible now.
Okay, audible. Okay, so now I can start then.
Yes, sir. You can. Sure, sir.
Okay. Good evening to all. So today I will talk about the magnetism. First magnetism, then magnetocaloric studies. So we shall straight away start. I think already 10 minutes lost. Yeah, okay. Now, audible now? Hello? Hello?
Yes, sir. You're audible
Okay,
now. Yes, sir.
okay.
Audible.
Okay, so we will straight away start. So we will talk today about the magnetism. So the plan of the talk is like this. I will give a brief introduction to magnetism, then different types of magnetism we will discuss, then origin of the magnetic moment and its properties, then theoretical aspect little bit I will touch about, Then finally, exchange interactions. So these are some of the resource material I have used. Most of them you might have already gone through. The solid state physics by Kittel, then magnetic materials by Lalit and Graham, then Stephen Blundell, magnetism in condensed matter, Peter Moore, magnetism in solid state, and some online resources for picture and other things. Okay, so what is magnetic? A magnet and magnetism, you might all of you might have experienced magnet and magnetism in our day-to-day daily life. Actually, it is a very, very old subject. It's originated from the Greek region. That magnet word originated from either Magnesia, that is place name, or from the people who have first experienced it. Actually, what historians are telling is that the shepherds, their shoe are attracted, their nails in their shoe are attracted to some magnetic rocks, naturally occurring rocks. Later, it was found that that rocks were magnetically attracting rocks were containing Fe2O3 force. That is the reason for that magnetism. So it's a very, very old subject. So now why we are studying magnetism? See, actually, okay, magnetism, why we are studying? Holding of practical use, practical potential, technological applications. Actually, magnetism touches a lot in our day-to-day life, everyday life. We are using the properties of magnetism. And second, from a fundamental theoretical point of view, magnetism, understanding magnetism in materials leads to the pertaining fundamental laws pertaining to the nature, because it's a purely quantum mechanical phenomenon. Okay, so practical applications, some of the practical applications is also most of you have experienced data storage. Maybe some 10 years back, hard disks were the main data storage for computer species. Now solid state devices are also there, but still hard disk data storage, long time memory, that magnetism is used. Then telecommunication, our mobile speaker. See the present audio also we are hearing through speaker that also contain magnets. Then TV, television set, and other things. Power electronic sector, generator, motor, transformer, coil, and EV, electrical vehicles. In future, it will be electric vehicles. There also we have magnet-based things. And a fan. There also magnet, either permanent magnet or electromagnets will be there. And various industrial applications. So industrial application, magnetic bearing. So you want to separate it to mechanical components. If it is metallic, you can use magnet for separation, magnetic separation, magnetic bearings. Then ferrofluid, it will have a liquid plus solid kind of thing. Magnetic solid for nanoparticles embedded in a viscous fluid kind of ferrofluid. And then materials there. Magnetic separators. And then medical, you might have heard of MRI, magnetoresonance imaging. Our human body internal magnetoresonance imaging we can do. And then MC, magnetocaloric effect, and MEG. MEG means magnetoencephalogram, like EEG for heart and brain. Traditionally, we are taking the electrical impulse or electrical signals of the heart and brain to diagnosis heart attack or brain tumor, other kind of thing. And magnetism also is using magnetic encephalogram and magnetic cardiogram. You can map the magnetic signal originating from either brain or heart for diagnosing a person like that. And then navigation, magnetic compass like that. So these are some of the applications. And then these are the typical magnetic field strength. This also, Earth magnetic field is very low. And then refrigerator magnet or its toy magnet, maybe a few millitesla. Then laboratory magnets, MRI machine of the order from Tesla. Then very large superconducting magnets, maybe up to 20 Tesla. Continuous use is there, continuous field production will be there. And pulse mode up to 60 and of the order of 100 also people are using in selected laboratories. Okay, so these are some of the importance of magnetic, some why we want to study. And problem with magnetism is its fundamental quantities. Many times it is confusing even for experts. And second problem is unit. If you go through different journals or different publications or different textbooks, there will be mixing of units. Some people will use CGS unit and some people will use SI unit like that. Okay, so here I will just briefly mention the three important fundamental quantities we often has to tackle for studying magnetism. One is the magnetic moment, that is a fundamental parameter. Solid state material, solid state magnetism, magnetic moment is the fundamental parameter. Then for large material is there, you can normalize the total magnetic moment either to the volume of the material or to the mass. That means magnetic moment, the total magnetic moment per unit volume or unit mass. That is known as the magnetization. The second quantity, magnetization. It's total magnetic moment over a unit volume or unit mass. Then the third is magnetic field. See, the first two, magnetic moment and magnetization, that for a solid state material, can be spontaneously generated or it can be generated as a response to an outside field. The magnetic field, that is an externally applied field, that is we are applying, externally we are applying. How we can apply the magnetic field is using either a permanent magnet or electromagnetic solenoids. And the third parameter is magnetic induction. And that is the sum of your externally applied field and the system's response. Now, okay, I will compare this. Magnetic field, H means it is a field that is equivalent to force. So you are giving a force to a system. And mechanical analogy, suppose we are giving a force, that is H, you are giving a force. And the system has to respond to that force. That system's response is M, magnetization M. And the total sum of your applied force plus system response, that is B. So H is equivalent to an applied force, you are giving a field to the system, and M is the system's response. System is responding to the applied field. System is responding and it is generating, either it is enhancing the field or it is reducing. So system has to respond to the applied force and the applied field, that is generating M. And B is the total sum of these two quantities. Then the other parameter generally we will susceptibility. Susceptibility means it is how much the system is susceptible to an applied field. So this is just briefly explained. So when a magnetic field is applied to a solid, the material responds to that field. Material's response is the magnetization. Okay. So we are giving a force, system is responding. And the total magnetic induction is the vector sum of the H plus and E. Now magnetic susceptibility. Okay, it is a measure of material's response. That means how much the material is susceptible to an external magnetic field. So simply speaking, it is the ratio of M by H, that is susceptibility. Suppose we are giving a magnetic field to a solid material and it is not giving any response. It is not giving any response. M should be 0 and your susceptibility should be 0. Okay, and the B mean is the total magnetic permeability. It depends on the applied field and M. Suppose M is 0, we are applying a field H and system is not responding. That means M is 0 means numerically H and B will be equal because whatever field you applied, it will be acting on the inside of the material. So B and M, H will be equivalent. It is not equal, but numerically it will be equal. So you can say it is equivalent. It is not equal. I am clearly audible now. So please call and inform if any trouble is there, whether in audio or video. Huh? Okay, I will proceed. Okay. Okay, now the okay. So in free space, the vacuum B will be equal to mu naught H, where mu is permeability. These are okay. You might have studied many times, so I will not repeat again. But actually, your permeability mu and susceptibility are related. In the next slide, I will show. So this is the relationship. See, you can see B equal to mu into H. That means mu 0 times H plus M. That H plus M is coming because mu 0 H is vacuum part and mu 0 M is the material's response part. So totally mu 0 into H plus M. So these are highly related. This susceptibility as well as permeability. Now this SI unit. See, you can see magnetic field and magnetic moment. Both have the same SI unit, but in CGS it is different. Actually, the problem with the magnetism different actually straight to different units. So these are the units. Okay. Now we will come to a solid state. Today we will basically talk about a solid state magnetism, geomagnetism, biomagnetism, or other areas. So we will only talk about solid state magnetism. So the main classifications and sub-classifications are like this. See, some material which may have magnetic moments associated with it. That magnetic moments either it can be interacting or it can be non-interacting. That will fall into paramagnetic, ferromagnetic, antiferromagnetic, that kind of categories. The first category, material which doesn't have an inherent magnetic moment. So materials which does not have an inherent magnetic moment, that will only response only it will give. When you apply an external magnetic field, that will respond to that externally applied field, and it will be always opposing to the applied field. That kind of materials is called diamagnets. Actually, that word dia means against or opposing. So materials which doesn't have an inherent magnetic moment, that will only respond to an externally applied field, and that response will be always opposing to the applied field. That kind of materials are called diamagnets. Now, the second category is material may have constituent electrons or neutrons or atoms or ions, which whatever be the constituent of the material, that have atomic moment, permanent atomic moment. There are two subcategories are there. One is these individual atomic or ionic moments are interacting. They are interacting via an interacting force or energy or medium, and then some exchange or correlated effects will be there. That will fall on the long range ordered systems like ferromagnet, antiferromagnet, ferrimagnet, or magnet. Material which doesn't show any interaction means that will fall under paramagnet. So paramagnetism means no interaction among the atomic moments, and ferromagnetism, antiferromagnetism, ferrimagnetism, or complicated ordering means there will be interactions among the constituent atomic moments or ionic moments. So ferro, antiferro, and ferri exhibit long-range magnetic order, and there are now other not so long-range order materials are there. Spin glass, cluster glass, superparamagnetism, that which is tiny. Okay, so the top right corner is the paramagnetism. Now long-range order, and okay, actually mouse pointer is not available. Okay. Maybe it is easy for you to understand. See, ferromagnetism means that long range order, all the spins will be nearby spins will be exactly the same direction, in parallel and the same direction. That is the ferromagnetism. Antiferromagnetism means nearest neighboring thing will be opposite, anti-parallel configuration. There also is exactly 180 degree. Collinear means it is called a collinear and non-linear antiferromagnetism. If the opposite moments are slightly tilted or canted, it is called a canted antiferromagnetism. Canted antiferromagnetism also shows some amount of ferromagnetic type behavior. Then ferrimagnetism also similar to antiferromagnetism, but the opposite moments will be unequal. So there will be a net magnetic moment. Then helical means it will be, say, from one lattice point to another lattice point, it will periodically, it will slowly shift or rotate to the magnetic moments. Then again, antiferromagnetism itself is several subcategories. These simple models I have shown here. See, type A means you can see that planar nature. That means in the inclined direction, nearby moments are coupled antiferromagnetically. But along the apoplane direction, it will be antiparallel. That is called A-type antiferromagnetism. Then the next is C-type antiferromagnetism means along the planar direction, it will be antiferromagnetic nearest neighbors. but out of plane it will be parallel, ferromagnetically coupled. And then the type G means for a single moment, so all nearest neighbors will be antiferromagnetically aligned. That means both in plane and out of plane it will be oppositely directed. That is continuity. Complicated types also are there, E type, S type, and P type. So now this is a classical example of the helical arrangement. You can see along the C direction, as you move along from one end to the other, slowly spins are rotating from the basal plane. Slowly spins are rotating, and from one place to another place, it will be completely fixed. So there are many examples. Classical examples. Phenomenal mode also. Spin density means periodically oscillating. Spins will be periodically oscillating along the direction. Classical example is chromium, another then DAP to AS2 systems like that. Then spin class, cluster class, and super parameters. These are not long range ordered, mostly short range ordered system or metastable systems. Generally, short range it can be either ferromagnetic or antiferromagnetic or electromagnetic. For short range correlations only will be there. No long range correlations. Spin class means mostly isolated pins or something like that. Cluster glass means oh, no voice is not clear. Hello?
Yes, sir.
Using a mobile phone, if I use that headset, will it improve? I will check with the headset.
Okay, sir. Okay, sir.
Hello, I will just check with the headset. Actually, PC I am using Linux and that also desktop. So audio. Hello.
Yes, sir.
Now I connected a headset to the mobile. Now any improvement is there?
Yes, sir. Yes, sir. Your voice is clear now.
Any improvement is there?
Yes, sir. Yes, sir. It is clear now.
Okay, so I will continue. Okay.
Okay.
Okay. So now that how the diamagnetics and paramagnetic such kind of material will behave in a measurement scenario. Generally, magnetic measurements, magnetization only measured, magnetization or equivalently magnetic moment. It will be measured as a function of temperature or as a function of field. That left graph, it is M versus T, magnetization versus temperature. And the second one, M versus H, is magnetization versus field. You can see for diamagnet, magnetization will be slightly negative. So it will be very weak negative susceptibility. And magnetization with respect to field also. When you increase the field, magnetization will fall down. Okay, and for paramagnet, trend is like this. When you cool the paramagnet at a low temperature, magnetization will increase. Actually, this curve, this trend is called 1 by T behavior. Magnetic moment of magnetization will be inversely proportional to the temperature. Here also, strong ordering will be there. And with respect to field, if you increase the field, magnetization will slowly increase, but still there will not be any saturation. And susceptibility will be positive and weak. Okay, now coming to ferromagnetism. Ferromagnetism, if you cool the first graph, M versus T, if you cool the material, initially it will behave like a paramagnet. Slowly magnetization will increase. And you can see below a TC, that critical temperature, below the critical temperature TC, actually it is called the Curie temperature. Magnetization will suddenly increase and it will reach the maximum value at low temperature. Actually, this behavior is called spontaneous magnetization. Spontaneous magnetization will be there below the critical temperature. Here, the main difference is spontaneous magnetization means this magnetization is generated even without applying an external field. Generally, for paramagnetism and diamagnetism, you have to apply an external field. H, you have to apply an external field, then the system will generate its magnetization or moment. That is the response only you will get. But here, the difference is ferromagnetism, even without an externally applied field, in the ferromagnetic stage, material can show spontaneous magnetization. And second is the initial magnetization curve. And the last figure number C is the full magnetization, which is hysteretic. Magnetic hysteresis will be there. And this will be the response for an antiferromagnetism. See here below the transition temperature Tn, it is known as Neal temperature. Below the transition temperature, antiferromagnetic ordering starts. Antiferromagnetism, that ordering will be opposite. So magnetization should fall. That's why it is falling. For a single crystal, perfectly aligned antiferromagnet at T equal to 0, all the moments are aligned antiferromagnetically means moment should be 0. But for generally for polycrystalline, random crystallographic directions will be there. So that's why it will not be exactly go to 0. Some examples of some of the materials are also there. Okay, and this is the ferrimagnetism. Actually, it is you can consider it as a mixture of antiferromagnetism plus ferromagnetism. So both components, there will be some overlap of both. There will be coercivity and hysteresis, and spontaneous magnetization also will be there. But okay, saturation needs very high fields. Okay, now this last slide I discussed about the magnetic properties. Now, okay, little bit. Actually, for an 1.5 hour, you cannot discuss all the points. So some of the theory part I also omitted. Okay. So now we will discuss the some of the microscopical origin of the magnetic moments. Okay. Actually, for solid state material, other than diamagnet, already there will be a magnetic moment associated with the atom or ion. That only either it will be interacting, otherwise it will be non-interacting. If it is interacting, it can lead to long range order. Now, what is the source of the atomic moment? That now we will see. Generally, magnetism or magnetic moment, it is associated with the current or movement of the charge. In electrostatics, electric charge is the fundamental quantity, and electric field is associated with charge. Similarly, for magnetism, magnetic moment is associated with current. That is the main contribution or movement of the charge carrier. Generally, in atom, electrons are revolving around the nucleus. So that is equivalent to a current loop or current circuit. So that is the main contribution. Orbital angular momentum of the electrons around the nucleus, that will give a magnetic moment. And additional magnetic moment is coming from the spin part, spin angular momentum. So there are two contributions. One is orbital angular momentum arising from the revolution of electrons around the nucleus. And the second one is the spin contribution, spin angular momentum of the electrons. Here we are only discussing about the electronic origin. Nuclear magnetic moments associated with protons and neutrons will be extremely low, and we will not discuss that in here. Only electronic origin we are discussing. Okay, so now this is just a little bit elaborated. What is the fundamental size of the atomic magnetic moment? Actually, you can think hydrogen nucleus. Hydrogen nucleus, you can think it has one proton and one electron. That electron orbital, it is known as the Bohr radius, first Bohr radius. So that electron is revolving in that Bohr radius, and that revolution creates a magnetic moment. that electron revolving around the hydrogen atom, it will give an angular momentum and consequently magnetic moment. That magnetic moment is known as the Bohr magneton. It is the fundamental unit of magnetic moment. So Bohr magneton. So one Bohr magneton, it is equivalent to the first orbital electron's magnetic moment of the hydrogen atom. Now the second part is spin magnetic moment. Actually, when you calculate the spin magnetic moment also will be fundamental spin magnetic moment also will be coming equivalent to one Bohr magneton. Okay. So similar to the orbital contribution, spin also will contribute, and the spin angular momentum is exactly same one Bohr magneton. Actually, the spin of electron, it is still ambiguous and what is called very difficult to conceptualize or understand. Okay, we have to take it as such. Okay, say it is like another degree of freedom. Whenever you are giving an energy to an electron or a atom, that energy can be utilized from orbital change from n shell to l shell, like that. Orbital change, that means position. It can change its position, or it can speed up, or its angular momentum part. It's orbital angular momentum or velocity, that kind of things. Another thing is spin. It can spin. It can change its spin. So it's another degree of freedom for energy transaction. That way only right now we can understand. There is no classical analog. Okay. So right now we have seen origin of magnetic moment for an individual atom, isolated atom or ion. So for a single electron, it will have orbital contribution plus spin contribution. So the total sum will be the vector sum of spin contribution plus orbital contribution. That means the total angular momentum J. J will be the vector sum of L and S. This is for a single electron. For a multi-electron atom, you have to add all the angular momentum and spin momentum vectorically. It will be a vector addition. So magnetic momentum of an atom in free space is proportional to the angular momentum J. So there are two relations. One is mu is equal to gamma J h cut. Actually, J h cut is the total angular momentum. It's a mechanical angular momentum related to rotation in classical physics. So magnetic moment will be related and proportional to the angular momentum. So equal to gamma J h cut, where gamma is the constant in one of the gyromagnetic or magneto-gyric ratio. Actually, it is the coupling ratio between the magnetism to the orbital part or rotation part. I can say magnetism and rotation. That coupling thing constant is the gyromagnetic ratio. Another thing is in terms of Bohr magneton, another equation is there, that is in terms of Bohr magneton, mu is equal to G, where G is the Landé G factor. Derivation you can find out any classical textbooks and magnetization textbooks. Okay, so for an individual atom, this is the thing. You have to vector sum, take the vector sum of and S to get J. See, here also there are two scenarios are there. Depending on systems or elements or materials or circumstances, there are two kinds of couplings are there. LS coupling and JJ coupling. In the LS coupling, all the individual spins will be added to give the total spin, and all the individual L component will be added to get the total L component. Then the total angular momentum will be the vector sum of total L plus total S. This is the LS coupling. And the other coupling scenario is JJ coupling. In this individually, we have to add the L and F to get the individual what is called the total angular momentum of the electrons, individual J. Then the final total angular momentum will be calculated using the sum of the individual J's. The LS coupling also termed as Russell-Sanders coupling. Okay, so many electron atom. See, actually this Hunt's rule and all maybe BSc or MSc level people might have studied, but this is the way electrons are filled, and based on the electronic configuration only we can study the magnetism, because that magnetism is highly dependent on the electronic configuration. For the same atom or same material, depending on the electronic configuration, its magnetic nature can change. That we will see later. See, the summary of this Hans rule is like this. That the three rules, 1, 2, 3, that I can quickly summarize like this. See, the first priority is always the electronic configuration is such that it should maximize the EF. That means electrons are arranged in a, whether it is P shell or D shell or F shell, generally SP, DF, up to this only we need. So mostly D and F are the magnetic material, D shell electrons and F shell. So for an D shell, if you are arranging electrons, the first rule is you have to arrange the electrons such that you have to maximize the S quantum number, spin quantum number. Then once that S is maximized, then the second is you have to maximize the L. Then the third is J. If it is less than half filled, then J will be L minus S. So more than half filled means L plus S. I will briefly discuss one or two examples, but okay, elaborating all this will be difficult, but one or two examples definitely I will show. This is again that many electron complications. See how much permutations and combinations can come. Simply for a S is equal to 3 by 2 and L is equal to 3 means there are a lot of configurations possible. How the L and S combinations lead to multiple J values, multiple total angular momentum. See, for the same orbital moment and the same spin contribution, that means for an atom having single S and a single L, depending on the electronic configuration, you can get multiple J values. That is the point. But Hans rule helps to clarify this. Okay, here I will briefly explain one example. Okay. So iron, it is atomic number, so it is 26. So if you write down the electronic configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p6, for 3d6, 4s2. Okay, this is the total electronic configuration. Now you can see iron 3 plus 2 plus 4 plus. See, iron 2 plus means that outer 4s electrons will go, or 4s 2 electrons will go. That means outer shell electron configuration will be 3d6. Actually, D shell has, D orbital has 5 subshell. That is the 5 square boxes I have put. Then, according to Hans rule, you have to maximize the S. That means first you have to fill all either spin up or spin down. Then only you will get the maximum S. Actually, this is where the Hans rule is coming into picture. How you can fill? See, 6 D electron means I can put first 3 box only I can put, and the remaining first three box I can fill. Remaining 2 I can empty also. Suppose I am filling first one 2, second box again one upspin and downspin, and third box also one upspin and downspin, means I can fill all the 6. The remaining last 2 I can keep it empty. But that is not the way. According to Hans rule, the first priority is you have to maximize S. How to maximize S means you have to fill all 5 boxes either spin up or spin down. I think you might be getting this, and maybe level people might have studied. I am not getting any feedback, so I don't know whether overqualified or I don't know. Okay. So right now, okay, I will explain like this. You can see 6 d electron means it will share 5 thing, and then that down electron, 6th electron again will come in the first box. So if you add a total, you will get S is equal to 2. And here for the system, that means electrons periodic table you might be knowing now. D electron systems generally spin part plus orbital angle, orbital part will give total angular momentum. But for a d electron system, generally L will be 0. It is called orbital angular momentum will be conjugate. That is another theory that I am leaving, but you can just simply take it as L equal to 0 for the d electron systems. Generally, not all. Spin orbit coupling is there, it will come into picture. But generally, only S will be there applicable. J, finally, J will be equal to S. L will be 0. It is called orbital angular momentum will be conjugate. Only rare earth ions, belonging to the block elements will be having very high L value. Okay, so the first row, I think you might have now understood, S equal to 2. Now, ion 3 plus means 3 electrons are gone, that 4s2 and one extra electron from the D will go. So 3d5, you can see 5 how it is arranged. Similarly, 4 plus means 4 electron will go, so it will end up with a 3d4. See, depending on the electronic configuration, you can get different S values. That means different moments. String 30 means it is completely filled. All the electrons are completely filled. You will not get any moment. So actually, for individual atomic moment, the criteria is partially filled or unoccupied levels, partially filled orbitals. Then only you will get. Otherwise, total sum of S will be 0. Total angular momentum sum will be 0. One sum is single. It will not have any. Okay, so here we have seen that iron has different electronic configuration. It will have a different moment. So the next thing is, even for the same ionic configuration, depending on the crystal environment, can have again different properties, different magnetic natures. Next slide, okay, I will discuss influence of the neighboring atoms. So you can see how the neighboring atoms are affecting the magnetic properties. So it is called crystal field effect or crystal field splitting. So here whatever the picture shown is the spatial symmetry of the orbitals. See, for an S orbital, the spatial symmetry will be spherical. That means for an S orbital electron, the probability of finding an electron along all the three directions, X, Y, Z, the spatial direction will be equal. So it will be spherical. Actually, according to quantum mechanics, that electrons called a cloud. Electrons will be chances or probability of finding only you can speak. So for an S orbital, that probability will be spherically symmetrical. In space, it will be spatially symmetrical. Electron. And for a P orbital, it will be dumbbell shaped. It will be dumbbell shaped along the X, Y, Z directions. Px orbital means along the x-axis you have maximum probabilities, maybe at some half distance from the origin along the x-axis, and similarly for the Py and Pz. So S will be 1, and P you have 3 orbital. P electron you have 3 cells are there, Px, Py, Pz. Similarly, for a d orbital, that is what the previous slide for iron we have shown 5 subshells. Actually, for an d electron, you have 5 subshells, dxy, dxz, dyz, and dz square, and dx square minus y square. You can see it's all the 4, it is like a double dumbbell. You can say compared to that p orbital, it is a double dumbbell kind of thing. These are the spherical probabilities, the spatial probabilities of finding the electron. See, here D, again 5 subshells are there. These 5 shells also again, depending on the symmetry, again classifications are there. That XY, XZ and YZ, that is named as T2G. Actually, this T2G and EG names are coming from the spectroscopy, that is spectroscopic splitting spectra and other things. So we can name it as T2G orbitals or EG orbital. Okay, so the next is okay, crystal field. See, given the crystal field, in figure A, you can see M is the transition metal like iron, manganese, cobalt, nickel, that kind of P element. You can see one iron or one transition metal is sitting, and it is surrounded by 6 other atoms. Mostly the metal atom and surrounding will be mostly oxygen. So for simplicity explanation, I will tell oxygen. So you can consider this as one transition metal sitting at the center, surrounded by 6 oxygen or 6 anions. 6 anions. See, this kind of arrangement is called octahedral arrangement. Octahedral. And the other thing is you can see it is tetrahedral environment. Tetrahedral environment. See that you can see the atomic arrangement. One metal and 4 oxygen atoms. And you can see for an octahedral and tetrahedral arrangement how the symmetries, that dx, y, or dz, how the d orbital and that dark shaded dumbbell is oxygen p orbitals, how the oxygen p orbital and the transition metal d orbitals are spatially arranged. You see, these two are not same, not symmetrical. So depending on the surrounding atoms, you will feel different electrostatic potential, or the what is called electrostatic potential will not be symmetrical. So to sum up, I will say like this. Suppose you have a transition metal sitting at the center. If the charge distribution around the transition metal is symmetric, there will not be any crystalline splitting. That means all the d electrons of the center transition metal will have the same energy level. Suppose transition metal is sitting at the center and charge distribution around it due to the neighboring atoms contribution. Suppose that the charge distribution is not symmetrical, then that transition metals d electron shell will be, that degeneracy will be splitted. Its energy levels will be splitted. Electronic configuration again, it will be splitted. See, here you can see how the energy levels are splitting. See, A and B are the octahedral and tetrahedral environment. See, in that 5 closely spaced lines at the left boundary is the free electron. That means if it is a symmetric, charge distribution was symmetrical, means all the d electrons will have the same energy. You see, depending on the octahedral or tetrahedral environments, that T2G and EG orbitals will be splitted. So this quickly I will sum up the past 3 slides. So this slide, what it is showing is the spherical charge distribution, spatial charge distribution of central transition metal ion. Suppose you have a transition metal ion, and how spatially its charge are distributed based on different orbital. So this is the charge distribution. Now this is the two different kinds of crystalline neighborhoods. You have one transition metal, how the neighboring atoms are located, neighboring anions, generally it will be oxygen, how the anions are surrounding the real transition metal. Depending on this surrounding atoms position on that electrostatic field, your in center transition metals d orbital energy levels will be splitted. Its energy levels will be splitted. So it will affect the, again the same example, iron 2 plus. Again the same example I will take iron 2 plus. Earlier we have seen iron 2 plus means it will be having S is equal to, because 6 electron, 4 will be unpaired, 1 will be completely paired, so S will be 2. Here we can see the same iron 2 plus electron, same iron 2 plus ion, depending on its neighborhood, depending its on neighborhood, due to crystal field splitting, again it can have a different electronic configuration. See, in the left, S is equal to 2. High state means you can see 6 electron, how it is arranged. First, T2G, 4 will go into the T2G, and the 2 electrons will be going into the EG orbital. That means earlier all the 5 shells, T2G and EG, were at the same level. But now, because of the neighboring atoms or surrounding atoms electrostatic field, degeneracy is splitted. D electrons energy are now splitted. So the electrons are finding different energy states. So ultimately, it will lead into different magnetism. The right figure you can see. Now, here all the 6 electrons are occupying in the T2G level. EG is completely vacant. So this is the S is equal to 0 state, low spin state. See, S is equal to 0 means it may not show magnetism also. You can see the same iron atom, same iron 2 plus ion, depending on the crystallographic environment, it can either be magnetic or non-magnetic. Okay, now I have to go a little slow, a little fast. Okay, this and all, okay, uniform magnetic field. Okay, I will quickly summarize this part. in a uniform electric field, suppose you have an electric dipole. You have an electric dipole, if it is placed in a uniform electric field, simply that torque will align the electric dipole along the electric field direction. That means the role of an electric field on an electric dipole is simply to align the electric dipole along the field direction. But opposite to the magnetism, here the role of a magnetic field, it will not align. See, it will not align the magnetic moment along the field. Actually, we are slowly saying it is aligning, but actually it will only allow precision of the magnetic moment at some direction. It will allow the precision of the magnetic moment, atomic moment. Magnetic moment is a vector direction, vector quantity. It will allow precision with the major component along the field direction. This is the difference between electric field and electricity and difference. Okay, and the second part is, okay, earlier we saw it will not completely align. Magnetic moment will not completely align along the field direction. It will allow only precision along the field. Whether all the angles are possible, no. Here also, that precision, that angle, that precision angle is specially quantized. Actually, your angle of precision will be specially quantized. According to classical theory, for a particular J value, any theta is possible. 0 to 180 or 0 to 360, any value is possible. But quantum mechanics, only spatial, it is called spatially quantization. Only specific directions only allowed. Okay, actually, this leads to the Curie-Weiss paramagnetism. Hello? Hello? Is there any problem with audio?
எத்தனை மணி லிஸ்டா
Please,
Hello?
participants,
Hello? Is there any problem?
ஃபர்ஸ்ட் சிங்கிள் எப்போ எடுக்கிறாங்க
participants, please mute your
Continue now. We can continue.
participants.
Okay, I am
Starting
continuing. Okay, I am
Charlie,
continuing.
ரெண்டு
Any
பக்கம் 6 மணிக்கு என்ன நம்ம
publish there, please call. The organizing part. Okay, so here, okay, Curie paramagnetism. I don't know background. If they studied magnetism means okay. Okay, I will just speed it up because time also 37. Okay, so this I will explain with a spin half system. That is the easiest one. See, that left figure you can see on spin half system. If you apply a magnetic field, that magnetic energy will be splitted. Magnetic energy, you can have a states. One is spin up state and spin down state. So these are the some of the theory part. Okay, I will quickly go through. This is Curie law. It is explaining the paramagnetism part. So magnet. Okay. So coming ferromagnetism, the main difference between ferromagnetism and paramagnetism is in paramagnetism, only temperature and external field only will try to align the magnetic moment. Magnetic moment will be aligned because of either thermal energy or magnetic energy. That means temperature and external applied field only role in aligning the magnetic moment. But in ferromagnetism and antiferromagnetism or perimagnetism, Peter Beers first proposed a molecular mean field. That means inside the material there is a molecular mean field. There exists a mean field. It will establishing a long range order. That means in addition to temperature as well as the externally applied field, there exists a molecular mean field. There exists a mean field which will try to align the magnetic moments. This is the source of interaction. Actually, this is some kind of empirical model only. So this derivation part I will skip. I will simply skip. Core idea is like this. One molecular field will be there. In addition to temperature and external field, there will be a molecular field that will try to align the moments. That will be the reason for the spontaneous magnetization also. And the Curie wise law is like this. Okay. Similarly for antiferromagnetism, so I will skip. Okay, antiferromagnetism. Okay, so this part I will explain. See, this is the summary of the three paramagnetism, ferromagnetism, and AFM. PF means EM means paramagnetism, FM means ferromagnetism, AFM means antiferromagnetism. You can see for an paramagnetism, 1 by chi versus T will be, all will have a slopes, but 1 by chi versus T will be passing through the origin, and antiferromagnetism, your 1 by chi will be higher, chi will be lower. And for ferromagnetism, your 1 by chi, inverse of susceptibility, that will be lower, but chi will be higher. See, these 3-4 slides I quickly skip it because this will be highly applicable to people working on specifically to magnetism only. They will only follow. General audience will not follow that much. Magnetism people, okay, they will be interested. Okay, now coming to the last part, exchange interactions. Actually, it is a very wide and large area. I will just briefly and quickly introduce some of the terminology. Interested people can further read because covering all will be very difficult. Okay, actually, exchange interaction. This is the fundamental reason for magnetic long range ordering. Ferromagnetism, antiferromagnetism, and whether it's radial or spin density wave or any kind of ordering, this is the source or reason. So exchange interaction, basically it is arising from electrostatic interaction. Actually, it is electrostatic origin and it is highly involved quantum mechanics, and mathematics is somewhat difficult. So exchange interaction, it is a quantum mechanically originated phenomenon and it is highly electrostatic in nature. So basically and fundamentally speaking, magnetism, its roots originated from the electrostatic and the Pauli's exclusion principle, and this mathematics I will skip. Actually, when two electrons are coming closer, see, you have the atoms. Atoms, you have many electrons, and when atoms are coming to form molecules, bonds are forming and molecules are forming. Mostly inner shell electrons will not participate in bond formations. So from individual atom or ion to bond formation, outer shell electrons only mostly participate. And so we will discuss mostly with outer shell electrons. In that also, outer shell electrons, whenever it is interacting to form a bond, two aspects are there. One is the spatial part of the wave function, spatial part of the wave function, and second is the spin part of the wave function. So the electron wave function, because of its symmetry, protection, and other things, if spatial part is symmetric, then spin part should be antisymmetric and vice versa. So from this criteria, actually it is originated from the Pauli's exclusion principle. Pauli's exclusion principle, and based on that only, whether electrons are coming closer or moving apart. If they are coming closer, that means if two electrons in a bond, molecular bond, if there is a chance that electrons are coming closer, means they can have a anti-parallel spins. That means one spin up, the second electron can go into down spin. Because that is the way Pauli's exclusion principle will work. Because spatially nearby electrons means its wave function should be, total wave functions should be antisymmetric now. So spin must be symmetric. And in the bond formation, suppose during the bond formation, if the wave function overlap is such that the electrons are far apart. Suppose the two electrons that are forming the bond, they are trying to stay far apart, then parallel spins are favored. That means that two electrons try to stay in the parallel spins. Actually, this exchange interaction is that is greater than 0 means triplet, and j less than 0 is singlet state. Okay, I will give some examples, but I don't know how much depth I can go. Okay, so this exchange interaction, I will give one brief example. So now different subcategories: direct exchange and indirect. Direct exchange interaction is very simple. The two interacting atoms are directly exchanging. Orbital overlap is large, so that suppose there are two iron electrons. Say we have seen earlier Fe2 plus and the other Fe2 plus or something. If the orbital overlap is large, means these two magnetic ions can directly interact. That means the outer bonding electrons can directly interact. That is called a direct exchange interaction. Indirect exchange interaction, that is the most widely seen. In the indirect exchange interaction only mostly seen. Indirect exchange interaction means suppose that bond is formed. Most of the time bond is formed in between one cation and anion. Generally anion will be oxygen, cation will be a transition metal, say iron, manganese, nickel, cobalt or whatever, or iron, whatever, and oxygen will be the anion. So the magnetic exchange interaction will not happen directly. So the bond will be like this: one transition metal, it will be bonding to one oxygen, and it will be bonding to the next transition metal. So between the two magnetic ions, there will be one non-magnetic oxygen will be sitting. So the exchange interaction will be mediated through one non-magnetic metal. That is called indirect. It is that simple. It is named super exchange because it is somewhat super. It's not a simple exchange. So it is termed as super exchange interaction. Most of the solid state materials show super exchange interaction. Okay, here I will try to give some simple explanation. See here the M means transition metal, say iron 2 plus or iron atom. O is oxygen, and another M, second M is another transition metal. You can see two transition metal bonded via one oxygen atom. The oxygen will be oxygen orbital will be p orbital, that is smaller circles that will be always very close. So the oxygen bond, that oxygen electrons, you can see spatially it is too close. That oxygen orbital electrons always try to stay in between region. See that electronic picture, electrons actually it is not static, it is highly moving close to the velocity of light, it will be moving. So in terms of quantum mechanics, we can only pick probability of finding the electron cloud. So for the oxygen anion, the probability is maximum in between the two bonded orbitals, in between the region. So that spatially that two oxygen electrons will come close together. So it will form anti-parallel. And that transition metal ion, depending on the bond length, how the transition metal oxygen bond are defined, bond length, bond angle, and overlap, electrons, that transition metal and oxygen bond electron, either it can stay close together. That means in between the M or bond. If it is residing most of the time, suppose finding the probability is more in between means, we may prefer anti-parallel spins. If it is preferring maximum, spatially maximum distance, if that electron, bonded electron, if it is preferring to stay spatially maximum apart, that means not close, then it will prefer forming parallel configuration. That leads to ferromagnetic interaction. Actually, this is purely electrostatic interaction and purely originated from quantum mechanics Pauli's exclusion principle. Because Pauli's exclusion principle, if you go through that quantum mechanics part, if the two electrons are spatially close together, they will always try to anti-parallel spins. If the electrons are spatially, if the electrons are coming too close, Pauli's exclusion principle always prefer anti-parallel. It will prevent from parallel configuration, especially close electrons. But if the electrons are far apart, then the exclusion principle will give a configuration, because that only will preserve your quantum mechanical wave function spatial symmetry. Actually, your quantum mechanical wave function has two parts. One is spatial part, one is spin part. Pauli's exclusion principle controls the spin part and spin symmetry. So because of that, your orbital symmetry as well as spin symmetry, both you have to take consider while forming the metal oxygen bond. So again, I will summarize like this. You have individual metal atom, individual oxygen atom. It is coming close together to form bond. So during the metal oxygen bond formation, atomic orbitals will overlap, and the overlap will be ruled by Pauli's exclusion principle. So the electrons will have a spatial part, spin part, and the symmetry rules will be there. And the Pauli's exclusion principle will be like this. If the electrons are coming closer together, it will prefer anti-parallel. If the electrons are far apart, it will prefer parallel spins. This you can work it out, because mathematics little bit it is not difficult. Even Stephen Blundell or uh, Little will have some explanation. Right now, the chalk and board I cannot further. But the interested people can go through Stephen Blundell. There is explanation here. So from the top and bottom diagram, I think now you can get some idea. So if the depending on the bond angle and the bond length, orbital overlap, where your bond strength and the electrons are residing in between the bond. In the top A, you can see two bonds are there, two M bonds are there. Actually, it is M O M bond. So the top figure AFM, you can see the left part, first MO bond is antiparallel. Electrons will be likely to reside in between the MO most of the time. And the second OM bond will be again the same situation. It is also antiparallel. That means electrons are trying to stay most of the time in between the metal oxide bonds. And the bottom figure, ferromagnetic part means that is second OM bond. There, that electron may be residing far apart. That is far apart. That is why it is preferring parallel spin. It is very simple to tell, but it is very complicated. Okay, I think okay, some people may got some idea. Okay, these are some of the empirical rules. See, actually, this previous slide we on that arrangement. Actually, how the arrangement is actually really happening. There are some empirical rules are there. These are empirical and semi-empirical. These are all observed and then formulated, and it is observed, experimentally validated by many experiments. So far, none of the experimental observation broken it, but still people don't know why it is followed. Actually, frankly speaking, from fundamental first principle calculation, it is still very difficult to study magnetism. It is very difficult to predict why fundamentally iron is magnetic. Iron is magnet, but some other element from the nearby is not magnetic. That kind of prediction very difficult. So most of the time, semi-empirical rules will be covered. So generally, the main rules I can summarize like this. That bulleted point you can see. The super exchange interaction between two magnetic ions with a half occupied orbital will be strongly antiferromagnet. Here also I try to give some examples in the coming slide. Okay, but how much I can convey, I don't know. Okay, and the second point is super exchange between an ion with a filled orbital and with a half filled will be mostly ferromagnetic. And the third option, uh, either half filled or filled versus empty orbital. That can go into antiferromagnetic or ferromagnetic, but mostly it favors ferromagnetic. Actually, the complication here is even bond angle matters, not only bond length. Even mild change in bond angle can flip the spin. Okay. So here is the summarizing whatever that good enough Kanamori rules. Actually, if you can understand the diagram, you can understand. I have given the reference of this diagram where I taken. Interested people can go through this article. Good enough memory. This is the summary. This is the summary of the exchange interaction. Actually, based on your bond, it determines whether it will go to AFM or FM, whatever. This people can understand this picture. You can understand. I will try to explain. Little bit complicated, but okay. I will try to explain. See, there are three cases: 1, 2, 3, and cations. Two types of cations are there: A and B. In that bottom column, they have given that picture explanation. See, for example, that middle oxygen is given. Oxygen is the anion. Oxygen is always anion, negatively charged ion with the filled orbitals p sigma. Oxygen will be filled and p sigma. In bonding, oxygen will be always filled. Metal B orbital only either half filled or vacant or fully filled like that. So it will be always antiferromagnetic. See, oxygen electrons, oxygen ions, so that electrons will be always stay close together. So they will be always antiferromagnetic. And the other two categories is A type cation and B type. Okay, A type cation occupied Tg and half filled, and B means it is occupied Tg, the vacant Eg. That means there is a difference between A type and B type in the occupancy of the Eg orbital. A type it is half filled, and B type it is empty. Eg orbital is empty. Okay, now you can come to case number 1, 2, 3. Case number 1, it is A versus A. That means your transition metal, both end transition metal in that bond, you have both half filled Eg orbital. This half filled Eg orbital means it will prefer strongly antiferromagnetic. Okay, and the second case is B versus B. That means empty orbital. Both sides it will have empty orbital. It will follow B antiferromagnetic ordering. And the third category, third case is A versus B. Please send the first mention name here. Oh, sorry, I can't help it. Okay, so the so the third category, A versus B. Here you can see half filled versus empty filled. That will be ferromagnetic. So these are the exchange interaction summary based on the bond. Interested people can go through the article. So actually there is a series of article, but this is the main article. Okay, one example I will show. Maybe this also one of the classical examples. Interested people can go further. See, LaMnO3, lanthanum manganate. This is a classical example. Lanthanum manganate, the strontium doping. You can see oxygen will be always. Does the angle between ionic affect this? Actually, angle affects. Sir, angle affects. Actually, angle, if it is 180, then it will be mostly antiferromagnetism. And deviation from 180, it may lead to ferromagnetism also. See, there is no general thumb rule. From system to system, it will vary. But what common observation is, if it is 180, antiferromagnetic ordering is preferred. If it is 90 means ferromagnetic ordering is preferred. It is not general. You cannot generalize. But deviation from 180, it will matter. Bond angle matters. Bond angle matters. Two things. One is nature of exchange interaction can be affected. Second thing is your exchange interaction strength will get affected. That means suppose you have a ferromagnet with a particular TC. Suppose you are changing the bond angle means exchange interaction strength can change. Consequently, your TC value can change. That means when you do the doping or applying pressure or something, or you are applying stress, if you are changing the bond angle, it can change the exchange interaction strength and it can affect the TC. On common sense logic, I will tell you. You have a one bond. If you increase the bond length, if you simply increase the bond length, the simple common sense scenario is it will reduce the exchange interaction strength. It will reduce the exchange interaction strength because you are increasing the bond length. So you are increasing the spatial interaction part you are increasing. So it will reduce the exchange interaction strength. At the same time, you are coming too close together. Exchange interaction strength will increase. This is the simple scenario. And you're changing the bond angle, definitely it will affect the exchange interaction strength. Okay, feedback and okay, I can share my mail, other things. I think that organizers can send the PDF to interested people also. Okay, that anyway we'll see later. You can communicate to my email also. Okay, right now I will continue. So this is one classical example. Okay, how much time I left? Okay, I will just go through quickly. Okay, so LaMnO3, you see this is the oxidation state. Lanthanum will be 3 plus, manganese will be 3 plus, oxygen will be 2 minus. So similar to that earlier Fe2 plus exercise, we can find out its spin state. S is equal to 2. S is equal to 2. Suppose now you are doping with a strontium. Strontium will be in 2 plus oxidation. So some of the lanthanum site you are doping with a 2 plus strontium. So in order to compensate the charge balance, some of the Mn, how much strontium you dop, that percentage of manganese will flip to Mn4 plus state. You see, manganese. Sir, please wait a time. Okay, that will be so. Okay, so Mn will be okay. So Mn will be shifting to 2 to 3 plus 3 by 2 simply because of doping. Okay, now we will see the interesting consequence. You see, the left side you can see it is Mn3 plus. Right side you can see it is Mn4 plus. See, here LaMnO3. LaMnO3 is only Mn3 plus, not Mn4 plus. Only Mn3 plus. That means you have a EG, one EG filled, half filled, and the other EG also half filled. See, unfortunately, that 3 plus diagram I am not showing. The diagram whatever I am showing is 3 plus versus 4 plus only. But you can imagine 3 plus versus 3 plus means both side you will have a half filled EG. So according to the Kanamori rule, half filled EG versus half filled EG means it will be antiferromagnetic. So LaMnO3, it is an antiferromagnetic and it is insulating. I will explain why it is insulating. Now, if you dope with a strontium, see, doping with a strontium, you now Mn4 plus is there. See, from Mn3 plus, you are getting Mn4 plus. See, Mn4 plus means S is equal to 3 by 2. I'm just quickly from the previous slide. You can see Mn3 plus is S equal to 2. Mn4 plus is S equal to 3 by 2. That means only 3 spins are there. In Mn3 plus S is equal to 2 means 4 spins are there. That is why you have one upper EG half filled. But in Mn4 plus, you have a 3 by 2. That means all the 3 electron will occupy T2G level. T2G level, and G will be vacant. G will be vacant. So according to the Goodenough-Kanamori rule, now the interaction is half full EG versus vacant EG. So here it can lead to ferromagnetism. So Mn 3 plus versus 3 plus means it is half filled Eg versus half filled Eg. That will lead to antiferromagnetism for LaMnO3. If you dose with a stone ship, you are changing the valence state of Mn. So now Mn4 plus ion is there. Their Eg is vacant. So that bond, that wherever that Mn4 plus ions are there, that bonds, you see that bond exchange interactions flip to anti-ferromagnetism, and totally the material will be going to ferromagnetism. Okay, now I will come to one is anti-ferromagnetic and insulating, and the second is ferromagnetic and it is now become a conductor. You see, not only magnetism changes, but its electrical property also changes from insulating to conducting. This also people can read, and I will explain little bit. Why it is conducting? You see the left and right figure, figure A and figure B. Now you see this Mn3 plus and Mn4 plus. Mn3 plus it is half filled Eg, and Mn4 plus it is vacant Eg. Only T2G are filled. Now there are also two scenarios are there, figure A and figure B. In figure A, you can see T2G all are up electron, Mn4 plus. For Mn4 plus, the T2G are all up. But for the B, I have shown Mn4 plus all are down. Basically, the B scenario is not favorable because if A scenario is there, that means if the second is Mn4 plus, if it is parallel spin, then that Eg electron that hybridization. Okay, I will explain maybe. Now I will continue. Okay, so you see that Eg, if it is parallel, scenario A was there, that electron can hop from one side to another. It can hop. Actually, that hopping means jumping. It is not jumping spatially, it is jumping from energy level, from one energy level. Actually, what ultimately it leads to electron movement to through the bond. Electron can move through the bond, and electron can move through the lattice, and it can give to the conductivity. That means if scenario A is favored, if it is ferromagnetically ordered, energetically it is favorable that Eg electrons can move from vacant filled to vacant position. That means it can go to conductivity. Scenario B was there. If it was antiferromagnetic, that second T2G was antiferromagnetically coupled. That electron cannot go into the vacant state because spin up electron can go only to the spin up vacant state. Again, Pauli's exclusion principle. If an electron is moving into a vacant position, spin up electron can go spin up vacant position. It cannot go into spin down vacant position. So Mn4 plus, if it is ferromagnetically aligned, electron can hop or electron can move. That is why it is now becoming conducting. So this system people can further read and explore. It is a classical example for studying magnetism. Okay, now these are further different kinds of exchange interaction. Okay, already time is there. I will not go into much. I will simply tell what it is. It is a spin orbit interaction. Since that orbital contribution will come. You can read further. I will only tell like this. Conclusion is it can that means tilting from linear collinear to tilted. It will lead to candid antiferromagnetism. It will tilt to the magnetization moment. Next is RKKY. This is for not for covalent bond order. This is metallic system. See, the idea I will explain. It is also vast area. Idea only I will explain. And here both ferromagnetism and antiferromagnetism is possible. This is mostly for metallic systems. That means moving electron system. Suppose one electron can move freely. Say one spin up electron. It is moving through the lattice. Say one spin up electron, it can spin polarize the lattice. That means if a spin up electron is at one position, it can polarize a region of spin down electrons to nearby area. That means on spin up electron, it is only mediated to conduction electrons. So one spin up electron is there. So through the conduction electron, it can polarize nearby spin down electrons there. So locally there will be build up of spin down polarity. That spin down polarity again can attract further a spin nearby spin down, like that spin up. Like that, chain of reaction can go. One spin up, it can spin polarize the nearby spin down. So local spin polarization will happen, and that local polarization further can attract another spin down. So you can the first spin of electron through the spin polarization can interact with the second electron. Like this, it will continue. So this is the basic idea. So people can further read. Okay, I think the first session I will stop hereby. Okay, I thank all my collaborator, colleagues, supporters, well-wishers, and friends. Without them, study will not be possible. And finally, I thank one and all, each one and all. So with this first session, I will stop. So I don't know. I hope there's some justification to the task. And the second, okay, start maybe after 5 minutes. Is it okay? I think the organizers can get the feedback from the participants, and if anybody further discussion or something, they can. I have some notes made up for class. But if somebody is really interested, I can share also. Anyway, I'm leaving the podium to the organizers. Maybe I will join after 5 minutes. Okay, I think the organizers can take up now. Next, I will continue after 5 minutes. Is it okay?
Okay, sir. Sure, sir. Thank you so much. We extend our sincere thanks to our resource person, Dr. Vinod K, for such a thoughtful, thought-provoking and informative session. And your valuable time and effort are truly appreciated, and we are grateful for the knowledge you have shared with us today. Thank you so much, sir. Now, the dear participants, we welcome you to take part in the discussion. Please feel free to ask, or you can raise the questions or share your views with our esteemed resource person. Okay, the feedback link also will be sharing it in the chat box. We kindly request every participant to fill it as earliest, as your feedback is very important in helping us improve and move forward. I hope after 5 minutes we can start the session again. So any queries or if you want to clarify something means you can ask. And after 5 minutes we can start the next session. And everyone please fill the feedback form meanwhile. Feedback form has been, the link has been shared in the chat box. So please, everyone, please fill it.
Okay, I'm ready. Organizers can give the feedback and I have to start. I'm ready only.
Sure, sir. Okay. Once again, I warmly welcome everyone to the second session of today's FTP, organized by Matandam College of Engineering and Technology. And we are indeed fortunate to have our esteemed resource person, Dr. Vinod K, with us to continue again and leading the session. We look forward to gaining more knowledge and insight from him. Now, I kindly invite Dr. Vinod K to take over the session. And thank, sir, please.
Okay, thank you. Okay, thank you. Okay, my slide and audio clear now.
Yes, sir.
Okay. Okay, so in the second section, it will be a little more technical rather than general. See, this is based on experimental research, mostly conducted in our own section. Okay, few outside thing I will show. So the title is like this: Magnetic/Magnetocaloric Studies on Selected Systems. So it will be little deeper into experimental experimental section. So my main collaborators are K. Jeevanandam, PhD research scholar, and my two colleagues, Reti Satyanarayana and Edward Prabhu from Africa. So I will just start. So the outline of the talk is like this. First, I will give a brief introduction to magnetocaloric effect, what it is. Then magnetocaloric studies on some selected systems I will show. DYSE2 system, La2NiMnO6 system, like that. Then some initial result on the copper doped La2NiMnO6 system. And then if time is there, I will show some additional data. Depends on the time. Okay. So we will start. So what is magnetocaloric effect? Actually, in the previous talk, we have seen magnetism. It is touching our everyday life, the lots of applications. So this magnetocaloric effect, another phenomenon effect related to magnetism, that is also future. It is a future technology. So first I will explain what is MCE. See, top box you can see it is a magnetic system or a magnetic system. In the absence of an external field, no external field is applied. It's a random magnetic moments will be random, completely random. See, for a paramagnetic system, paramagnetic system, without an external applied field, moments will be random. See, entropy, entropy is a concept which is related to randomness or disorder. If system is disordered or random, then entropy will be more. Ordering means entropy will be less. So entropy is related to ordering or randomness. So the first figure you can see, in the absence of an external field, magnetic moments will be random. And the same system you apply an external field. Bottom figure, now you can see we are applying an external field. So the moments will try to align along the applied field direction. That means by the application of an external field, you are changing the spin entropy. You are changing the spin ordering or spin entropy. So for a random spin, spins are high sorted, high magnetic entropy. You apply filter, spins will be ordered, magnetic entropy will be lower. And for any adiabatic system, adiabatic thermodynamic system, the turning equation is like this. Total change in entropy for an adiabatic system will be zero. That means for an adiabatic process, if some change of entropy is happening somewhere, then the same entropy, same amount of entropy should be reduced at some other place. Then only it will tally. So you can see an application of magnetization, magnetic entropy is falling. So consequently, what is the other entropy in a solid? See, solid have a magnetic entropy will be there, lattice entropy will be there. And in addition to this, electronic entropy will be there. That is, compared to this lattice and magnetic contribution, electronic entropy will be negligible, so that we will not consider. So generally, the main two entropies are lattice entropy and magnetic. Magnetic entropy is coming from magnetic spin ordering. Lattice entropy is related to lattice vibration. See, atom have a lattice vibrations will be there. Atoms will be vibrating. That vibrations will be the lattice entropy. Now you can clearly see lattice entropy is reduced with the application of magnetic field. compensate that, lattice entropy should increase. Lattice entropy should increase means atoms are supposed to vibrate more. That means if spin is ordered, then atoms will be vibrating more. Atoms vibration means simply means it is increasing the temperature. Because temperature means it is atom vibration means phonon. So you are reducing the magnetic entropy, increasing the phonon for thermal energy. So the summary is like this: whenever an adiabatic field change occurs for a magnetic system, its temperature changes. So magnetic field can control the temperature of the machine. This principle is called magnetocaloric effect. And why it is important, we will see. So why it is important? So it can be used for magnetic refrigeration. Here I have shown on 4 cycle schematic magnetic refrigeration process. Ordinary refrigeration, you people may be knowing, in our home we have refrigerator or fridge. There what we are using is, we are compressing and decompressing, compression and depressurization of gas. You are compressing a gas, then decompressing it. Adiabatic and isothermal process. That will generate cooling effect. Here equivalent to that, equivalent to gas compression and decompression, here what we are doing is adiabatic magnetization and adiabatic demagnetization. Okay, I will explain the figure. Top left, it is T. T means at a particular temperature, your random magnetic moment, no applied field. Now, going down, adiabatic magnetization. You are applying magnetic field. You can see top, from top left to bottom left figure. All the spins are ordered. That means magnetic entropy is reduced. So consequently, your temperature should rise because lattice entropy will increase. That means your temperature is increased by an amount delta T. From T, now we have T plus delta T. That increased amount delta T, that we are now removing the heat exchange through some heat exchange process that I will just briefly explain. So the heat exchange you are removing. So the system now reached initial temperature T with the ordered moments. Moments are ordered. Now you are adiabatically demagnetizing it. Now you are removing the magnetic field adiabatically. See, when you remove the field, moments will go back. Moments will again go back to a random. Now the reverse process. You are randomizing the moments. You are increasing the magnetic entropy. So consequently, lattice entropy will fall down. That means temperature will fall down. See, from T, you go to T plus delta T, then again T. Now we are reaching T minus delta T. That means your initial magnetic solid, that is now in a lower temperature. That lower temperature, that reduced temperature thing, you connect it to your load, whatever load you want to cool. With the heat to that, now your load will cool and the whole cycle will be repeated. This way, by repeated adiabatic demagnetization, you can cool the sample. So this is called magnetic refrigeration. See, this first two process I have combined as an isothermal way. You can do first two process. That means from disordered T to ordered T, you can reach. Okay, and this top right figure, actually it is the temperature, temperature versus time curve. Yes, temperature versus time. X-axis is time. See, before and after the adiabatic demagnetization, the temperature of the total system. Initially, it was at a higher temperature, higher equilibrium temperature. At the moment you do the adiabatic demagnetization, spin temperature falls down, spin entropy falls down. Consequently, lattice temperature also will fall down, and the system will settle down to lower temperature, lower equilibrium temperature. This cycle you can repeat. See, why it is important? Simple. It is, you can use for cooling application. Some application scenario I am describing: room, vehicle, food, industrial. Potential low temperature. See, low temperature. Right now, magnetic refrigeration or adiabatic demagnetization is the cost-effective and viable technology. Low temperature means millikelvin range. I am talking about millikelvin range. See, the millikelvin range. This is the most cost-effective and viable technology people are using worldwide for low temperature, ultra low temperature, not room temperature. See, what is the advantage? See, this is the advantage. Green technology. Now the world environment hazards are there environmentally. See, ordinary refrigeration technology, it is based on gas vapor compression. And whatever gas you are using is the hydrocarbon, fluorocarbon based things. That is environmentally hazardous. That will deplete our ozone layer. Actually, ozone layer is inevitable for even human life sustainability also. So that environmental hazardness is there in conventional gas-based cooling technology. So the world itself is slowly thinking alternate cooling technology. One viable future research area is magnetocaloric effect. So environmental safety is the biggest advantage. Some proof of concept and trial laboratory level. Some are already, I think, people have some commercial scale also it is there. Not for household or something because household still cooling power requirement is more. But for food technology and other things where even 2 to 5 degrees Celsius below room temperature is okay. And the cooling power also not that much where people have employed this. See, cooling capacity up to 15 kilowatt industrial scale people have designed. Maybe you people can go and search in YouTube. There are several YouTube videos are there, demonstration videos and other application videos are there. This is an emerging field, so you can get more information. Wikipedia and YouTube. Here we have a constraint about copyright issues and other things in Wikipedia. And here, low temperature, especially space application and low temperature, satellites regularly use the magnetic refrigeration. Adiabatic demagnetization, that is the keyword you can search. Satellites regularly use this because for satellite, satellite, the important working advantage is it is using in space. In space, the ambient temperature is itself is cold. Space itself is cold. See, in Earth, we have the room temperature around 27 degrees. That means around 300 Kelvin. This is our ambient temperature. In space and outer space, satellites where ambient temperature is around 4 Kelvin or 10 Kelvin or below that, around helium temperature. So there, from 4 Kelvin to million Kelvin, you can quickly cool using adiabatic demagnetizing technique. Then people are using, this is regularly using. Susaku is the Japanese satellite. I think this you can check in Wikipedia. Their sensor array, they are using to 60 millikelvin. See, from millikelvin to microkelvin, adiabatic demagnetization, people are using. Paramagnetic salts, people are using. Mainly gadolinium based things are using. And this is another emerging area, biomedical area, where magnetic drug delivery, precision drug delivery to targeted cells. See, here the idea is you can coat to the drugs, medicine with some low melting plastic or some kind of polymer and embedded with a magnetic nanoparticle or magnetic particle. And then you can move the drug ions or this whole assembly to the targeted cell area and you apply magnetic field locally. That magnetocaloric nanoparticle or material will melt it and it will melt to the drug coating cover. That drug will be covered with a low melting polymer or something. So the drug will be precisely delivered to the target cell area. And see, technically speaking, it's much better technology for treating cancer and other things. And here the thing is that magnetic material should be biocompatible. So right now, I think it's iron oxide based things that people are using, but this is an emerging area. Okay, now going to technical details. Okay, people who can understand, okay, follow. Otherwise, we can simply ignore these 2 3 slides because it is highly technical. Okay, magnetic caloric effect. How you will quantify it or how you will characterize it? Because in the previous talk I mentioned, generally we will study magnetic moment or magnetization. That also experimentally we will measure magnetic moment. as a function of temperature you can measure, or field you can measure, or as a function of time, pressure. These are the general variables. So you can measure the magnetic moment. But to study the magnetic caloric effect, see, you have to characterize the thermal response under a magnetic field. Straight away, direct method is you measure specific heat under magnetic field. But specific heat measurement itself is time consuming and difficult. Again, specific heat measurement under magnetic field, again time consuming and difficult. So for quick characterization, for initial material characterization, you can simply depend no specific heat measurement. You can simply depend magnetization measurement itself. But that is an indirect method. You have to derive or estimate the parameters from the magnetization data. The main parameters are: one is isothermal magnetic entropy change, is extracted from the magnetization versus temperature data. Second is adiabatic temperature change. Third is the relative cooling power, RCP, or one more equivalent term is the refrigerant capacity, relative cooling power and refrigerant capacitance. Both are the equivalent term, but not equal, equivalent term. That characterizes how much strength the cooling capacity or cooling material. In figure, I will simply explain. See, people who cannot follow this, they can ignore this because this is technical. They can concentrate on the results part also. But for the sake, I will explain this figure. The right figure is explaining temperature versus entropy for any general magnetic material for two magnetic field. H1 is a lower field, H2 is a high field. You can see delta SM T comma H line. That means you are applying a magnetic field H1 to H2 isothermally. Temperature is same there. Entropy is falling. That means isothermally you are applying field. That line the magnetic material will follow. In the entropy versus temperature curve, that line your material will follow. And the delta T, T comma H line, that is the line if you are applying magnetic field adiabatically. That means if you are applying magnetic field, you are increasing magnetic field from H1 to H2, then entropy will be same, but your temperature will increase. Actually, this is the same thing initially I explained with that isothermal magnetization and adiabatic magnetization, that figure. But this is a little more okay. So magnetization. How we do the thing is, you can see that figure. Magnetic isotherms are there. Magnetic isotherm means M versus H data measured at different temperature. So you have to measure the M versus H data at different temperature. Then using that equation, delta Sm is equal to mu naught integral by dot T to dH. This you have to do. See, you have to take the derivative of magnetization with respect to temperature, then integrate with respect to field. Then you will get the isothermal entropy. See, it is a calculation part. So that equation simplification and other thing you may say how you are doing. But this is the equation. It is called a Maxwell's equation. Maxwell's equation. Okay, now this is how you are defining relative cooling power and refrigerant capacity. So once again, I will tell from experimentally you will measure M versus H for different temperature. From this, you will reduce the delta S. Then delta S you can plot for different temperature. That is called delta S versus T curve. This is a typical delta S versus T curve. This I have shown just for showing the trend. So for a delta S versus T curve, it will look like this for a second order ferromagnetic sample. It will have a maximum value around its ferromagnetic transition. It will be a what is called a peak shaped curve. Now, how you define relative cooling power? The relative cooling power and refrigerant capacity are equivalent but not equal. See, relative cooling power is defined like this. In that figure, you can see the parameters. You take the maximum delta S value and multiply it with the full width of maximum. Actually, it is the area including that gray region. Area in the curve including gray region. Maximum into full width of maximum. Now refrigerant capacity means it is the integral area from the T1 to T2. T1 to T2 means it is the full width of maximum, lower part and upper part. Actually, it is the area excluding that gray region, including only the patterned, that is slash the patterned region alone. So generally, you can see refrigerant capacity will be lower to relative cooling power. Actually, both are area and both are quantifying how much will be the cooling potential or cooling capacity or cooling effectiveness of the material. How you define that only matters. Okay, now I will go into the result part, experimental result part. These are the work done in our own lab. You can see further details in that attached reference also I have attached. DYSC2, this as far as I understand, only one report is available, that is from our lab. The problem is DYSC2 synthesis is extremely difficult. You cannot do the synthesis of DYSC2 by normal methods. Problem is dysprosium, it is a very high melting rare earth, very high melting, and selenium, it is a very low melting. Around 600 itself, selenium will melt, and it will have very high vapor pressure. See, if you heat treated selenium and dysprosium together, at the end of the heat treatment, all the selenium will be gone. You will not get any DYSC2. You will get only dysprosium. Selenium all will be. So how to synthesize? See that we have made some special dot locking chamber. Ordinary furnace, tube furnace, vertical tube furnace we used, but we designed a load locking chamber using stainless steel, and in that we have locked high argon gas around 30 bar, and that only we used for synthesis. So during the synthesis, your high pressure argon will suppress the selenium loss, but still it is very difficult to do synthesis. In the time, amount of selenium loss you cannot control, and the final stoichiometry is horrible. Even we now left completely this area to my two synthesis attempt. See, this is the structural property. See, structure, I think it is tetragonal. Tetragonal structure with the atom positions. Okay, magnetism, it is antiferromagnetic. You can see it is typical antiferromagnet around 4.7. Actually, pure antiferromagnets are not good for good magnetocaloric. But why we studied this is we have earlier some experience with the European selenide, EUSC, that I am not shown. That showed some metamagnetism. Metamagnetism means some antiferromagnets, when you apply the field, it can flip the spin. Antiferromagnet generally it will have opposite moments. But some antiferromagnet at some high field, that opposite spin, it can flip with external field. It is called metamagnetism. That okay, this is a TC variation. This is the thing. This is the metamagnetism. You can see at some point it will flip and it will behave like a ferromagnet. The metamagnetic transition to antiferromagnetism to ferromagnetism or candidate antiferromagnetic. In the metamagnetic transition region, your entropy will be more because metamagnetic transition means again ordering is changing. So there will be a huge change in the magnetic entropy. So this is simple measurement details. We have collected magnetization versus field experimental data, different temperature. Now this you can convert into thermal entropy change. So this part actually this is another area. This anyway I'm not going to detail that Ginsberg land. Initially I thought of putting Ginsberg land analysis the first part, but since already it is too much, I skipped. I completely removed that. It is another area. It is another metaphor. This is delta SS versus T curve, typical MCE curve. Here the value is around 11.8 joule per kg Kelvin. Not small, but moderate to high range. This is the RC, refrigerant capacity. You can see around 310 joule per kg. This is also around moderate. So one thing I will tell you, this DYSE2, it is a low temperature material. See here the transition is low temperature, around 3 or 4 Kelvin. So this main industries, it is a low temperature say 3 to 10 Kelvin, 3 to 50 Kelvin, like that. Low temperature magnetocaloric material. So moderate refrigerant capacity. That is the conclusion. Now I will come to a double perovskite La2M and NiO6. It's a near room temperature material. So near room temperature magnetocaloric. Okay? So interesting structural and magnetoelectric properties. So ferromagnetic semiconductor. So generally, bond ferromagnetic material will be metallic. Ferromagnetic material will be generally metallic. Very rare only to find ferromagnetic semiconductor or ferromagnetic insulator. La2NiMnO6 is special because it is a ferromagnetic semiconductor and also critical temperature close to room temperature. So we will explore its magnetic caloric, initially magnetic property. So these are some simple explanation. See, double perovskite, single to perovskite. Actually, perovskite means it is a family of materials collectively termed as perovskite. Here I am explaining based on a cubic lattice, but it need not be cubic. It is only for schematic. Actually, it contains almost all the crystal structure. I will explain the figure. You can see that colored big thing, lanthanum, at the center of a cube. I'm explaining with the top left figure first. You can see the cube, you can assume a cube. This is only for explanation. Reality is different. It may not, need not be cubical. Lanthanum will be at the center. Manganese will be at the edges. No oxygen for the left central figure. Sorry, left top figure. Now I have added oxygen. That is a top right figure. You can see each manganese will be surrounded by 6 oxygen atoms along the A, B, C crystallographic directions. Or you can assume X, Y, Z Cartesian coordinate. 1 plus X plus Y minus Y plus Z minus Z. Like that, 6 oxygen will be there. Now I have drawn the left bottom figure with the octahedra. You remember in the first talk we have discussed about octahedra. This is one example. So this is LaMnO3. Like that LaMnO3, it will repeat all the 3 directions you to get the crystal structure. Actually, this is a single perovskite crystal structure. So you see LaMnO3. Actually, this is LaMnO3 is left. LaNiMnO3, La2NiMnO6 is a double perovskite. That transition I will explain. See, okay, that slide I missed. Okay, fine with this. See, LaMnO3, this is single perovskite. If all the 3 directions, it will expand to get the unit cell. Suppose one of the manganese site you are replacing with a nickel. Now you see, because of symmetry, your primitive unit cell is now doubled. Earlier it was small primitive. These are primitive cells. You see left is one single perovskite primitive cell, LaMnO3. Now one manganese site you removed and replaced with a nickel site, and it is now it is perfectly ordered, means your symmetry, due to symmetry, unit cell, primitive unit cell volume is doubled. That is why it is labeled as doubled perovskite. And now the stoichiometry you can La2NiMnO6. This is perfectly ordered. I will show you there is another way to get La2NiMnO6. Here you see La2NiMnO6, it is a perfectly ordered. The other thing is it is disordered. That means manganese and a nickel is not perfectly ordered. Manganese and nickel sites are randomly ordered. See, left, each manganese will be surrounded. On manganese, after oxygen, its neighbor will be nickel. That means manganese, there is a neighbor will be nickel. It's a perfectly ordered. That will form into monoclinic. And the other possibility is orthorhombic. There, manganese, its neighbor can be either a manganese or a nickel. But the total number of manganese and nickel will be same. Total, if you add total n number of nickel and n number of manganese, total 2n, that will be same. But the ordering will be random, completely random. these two will have a different crystal structure, different magnetic property. Because now in your nearest neighbor exchange interactions are changed. See, bond you are changed now. Your metal oxygen metal bond is changed. In the left case, it is always metal oxygen metal bond is always like this. Manganese oxygen nickel. Always manganese oxygen nickel is the bond. So your exchange interaction is fixed with that. The second one, right side figure, you can have a manganese oxygen nickel bond, manganese oxygen manganese bond, nickel oxygen nickel bond. So it is complicated. You see how you can control it. One way is synthesis temperature. What we observed is if you do the synthesis at a very high temperature, chances of disorder is more. If you do the synthesis at a relatively lower temperature, ordering is favored, but then the reaction completeness also a problem. So this is the result. Ordered low temperature synthesis means it will be ordered monoclinic. Magnetic transition will be around 70 degree. That only we will concentrate more further. The ordered monoclinic around 270 Kelvin, it is a ferromagnetic. Routine measurement, magnetization versus field. Simple isothermal magnetization data. This we can convert into heat capacity. Sorry, magnetocaloric data. Here we have shown isothermal entropy change, refrigerant capacity, and adiabatic entropy change. That is actually for adiabatic entropy change, you need heat capacity. For the present work, we have done some calculation. That is why that symbol plus this is the line also. The line is based on calculation. That calculation part I skipped. Okay, now the next part is copper doping. Here magnetocaloric part, I think I will not go into detail, but magnetization part, magnetic part I will just cover. See here the thing is nickel 2 plus. Okay. So nickel is 2 plus and copper is, nickel is 28 and copper is nearby 29 atomic number and slightly higher radius. Copper is slightly higher in that octahedral element. So this is the result. You can see as expected, lattice volume is increasing. This is as expected because you are substituting with a slightly larger ion. And now the magnetization data. See, you substituted with a slightly larger ion. And one more thing is nickel spin value is S is equal to 1. Copper spin value is S is equal to half. So the magnetic moment also different. So this is the magnetization data. You can see as you increase the copper content, slowly transition temperature is reducing from 270. You can see as you increase the copper content, as you increase the X, transition temperature is falling down. So here transition is fallen down and it is broadened. And at a low temperature, at a higher copper content, some additional feature that I will explain. It is a spin glass. So it is spin glass or cluster glass formation is there at very high content. And for the end compound, La2Cu MnO6, we observed no ferromagnetism, only spin glass nature we observed. Okay, so this is the Curie wave fit analysis. This is also a little technical. So here the interesting thing is for the lower copper content, it is following the ferromagnetic trend. As you increase the copper content, there is a deviation from the Curie wave law. What it means is, it is called a Griffith phase that I will explain later. And the end compound, it is spin glass. That also schematically I will explain briefly. Okay, so this is the schematic phase diagram of temperature versus composition constructed. You can see depending on the copper nickel ratio, depending on the copper nickel ratio and the temperature, we can have paramagnetic to ferromagnetic transition, and GP means Griffith phase area, spin glass, SG means spin glass. So this is phase diagram covering different aspects. Okay, so this is the schematic explanation. What are the different areas? Paramagnetism you all know. all the spins will be completely random. So if you look in a spatially extended region or a spatial region, you can see the spins are completely random. So totally averaging zero magnetization. Ferromagnetism, it is completely aligned in one direction. Spontaneous magnetization, all the magnetic moments are aligned. So you will get a full magnetization. Griffith space means, okay, actually here also I need a pointer, okay. Griffith space means it's a paramagnetic matrix. That means the main phase will be paramagnetic. In the paramagnetic matrix, there will be localized ferromagnetic components. That means localized small short range ordered ferromagnetic pockets are there in the large paramagnetic matrix. It is neither fully paramagnetic, neither fully paramagnetic. Long range ferromagnetic order is not developed. Only some pockets are ferromagnetic. Some short ordering is ferromagnetic. See, actually, why this is happened is related to that earlier slide I was explaining ordered versus disordered. Depending on the disorderness, you will get a local short range ferromagnetic order or paramagnetic disorder, that kind of thing. Because of that, you will get a Griffith space. And the last end compound, you get a spin or cluster glass. Spin or cluster glass means there will be local ferromagnetic ordering, but that also not entirely along all the cluster will be along the same direction. See, some cluster will be ordered in some direction. The other cluster, it will be ferromagnetic ordered inside that cluster. But that cluster will be on a large area, it will be again ordered in some other way. So your total moment again will be very lower. That means you can say it is a random ordering of small ferromagnetic clustering. That is the thing. There will be correlations. There will be correlations that only we can tell. So short range ferromagnetic ordering will be there. Clusterings or pockets will be there. And these clusterings, in between different clustering will have a different work. So total it will have a low moment. And these spin plus other things that will have interesting magnetic properties, theoretically interesting. Okay, now we have some calculations based on Ising model. Actually, the reasoning is we have to understand why the spin model, why the temperature is critical temperature is reducing. That is one thing. We are substituting copper at the nickel site. So how the exchange interactions and how the TC result shows TC is reducing, transition temperature is reducing. How it is happening? For that, we have done some calculation basing on some mean model analysis and Ising model. Detail I will not go. Simple Ising model is like this. Nearest neighbor exchange interaction. You can see left A figure means primitive unit cell. B figure means we have removed all the non-magnetic ion. Only magnetic nickel and manganese is shown. Non-magnetic lanthanum and oxygen removed. The nearest neighbor interactions I have marked with arrows. You can see how the nearest neighbors are there, and these nearest neighbors will interact. You see the nearest neighbors, it is not even many nearest neighbors are there. I shown only one pair. Actually, you can see each nickel will have 6 manganese and vice versa. And each manganese will have 6. Not all will be 90 and not all will be 180. There can be mix of bond lengths. Okay, so here is the results of the A figure is the results of the Ising model calculation, Monte Carlo simulation, and B is the comparison of experimental data, Monte Carlo simulation data, and the mean for the calculation data. Here, see, actually in between I have done some other experiment. It's called XAFS, extended EXAFS study. where I got the conclusion that bond length and bond angle is not that much changing. Bond length and bond angle, especially bond angle, it's not deviating with the copper substitution. It's almost identical. So the next possibility is spin. You can see that nickel is a spin S is equal to 1 and copper is equal to spin is equal to half. So I have done all the calculation assuming same. See, here exchange is J exchange is the exchange interaction. Here I have considered all the exchange interaction identical, irrespective of copper content. Only I varied the spin part because nickel is S is equal to 1, copper is equal to S is equal to half. So spin part I varied and I did the calculation, and the result is it is agreeing more or less with the experimental. So the conclusion is magnetic dilution is the reason for the TC decrease. So you are diluting spin S is equal to 1 with the spin is equal to half. So that in the bond you are diluting one of the magnetic ion that is affecting your exchange interaction strength, and that is resulting in the reduction, TC reduction. Okay, now the end compound La2CuMnO6 is a spin glass system. Here I will only show one of the characteristic nature of the spin glass system. It is memory effect. That means it can remember thermomagnetic history. Technical detail and experimental detail, too much I will not go. Here the procedure is like this. You can cool the material with a field cooled protocol. That will be the reference. Then you can field cool protocol, and then you warm the material above your freezing temperature, spin freezing temperature. That cusp or peak point is called spin freezing temperature. Switch off the field, then not switch off. Then you cool again the sample, and in between you stop, wait, and pause there for a few hours, say 1 hour or something, and switch off the field, so that you are switching off the field in the field cooled position. So definitely moment will fall down. That is the field FCC stop circle that data. Your field cooled thing, you are switching off the field means definitely moment will fall down. Like that intermediately, then again apply field, again cool, wait for some other temperature, again switch off the field like that. Reach the lowest, then again you warm. Wherever you are stopped, switch off the field and stopped, there it will remember that temperature, it will remember. That is the memory effect. Actually, the three main point is like our life. It has aging, rejuvenation, and memory effect. Actually, interested people can go through this article. These two articles, these are describing more about the spin glass nature and its physics. Actually, spin glass, two, three different theories are there. This is the one which I found convincing to me. A random vacuum and the metastable states. Actually, that Ginsburg-Landau theory, if you go through, uh, during ferromagnetism, spontaneous magnetization will develop. So it will, your free energy curve you can see. Here, instead of one free energy minima, you will have multiple free energy curve. These details people can go through because this is an involved area, to go into deep involved area. And this, okay, this part also, okay, I will just quickly go through. These are some additional work, sample geometry dependence. See, same sample, depending on which direction you are applying the magnetic field, you will get different magnetic moment. Actually, it is called a demagnetizing factor, depending on the geometry. When you apply the magnetic field to a material, depending on the geometry, it will have internal polarization. That is called a demagnetization. Because of that internal magnetization, actual internal field fed inside the sample will be different. That means again, I will brief like this. H external is your externally applied field. Because of the sample polarity developed inside the material, that is highly geometry dependent, it will develop a demagnetizing field HD that will be opposite to the applied field. So in effect, the actual sample will feel only H internal, that is H in. That will be dependent on the field geometry. Okay, I will just quickly go through because we want to know whether this geometry will affect ultimately your MCE. So this is the different, you can see for one sample here 103 for different sample size, different direction, magnetization is different. Consequently, you have a different delta S versus T curve. So the result I will summarize like this. Depending on the Dmax factor for different geometry for the same sample. That means for the same sample, depending on the geometry, you have to apply demagnetization correction. So relative change will be there. That will be in entropy. Okay, actually entropy and relative cooling power. Okay, that. So you will have a different entropy. Okay, so the next is again another simple topic. Okay, this is related to sample inhomogeneity. Whether the sample inhomogeneity in the form of sample spread, because when you prepare the sample, especially polycrystalline sample, inhomogeneity is inevitable. You will not get the sample characteristic same throughout the entire volume of the sample. And the most important factor is some TC spread, transition temperature spread. Even in the previous copper doped thing, you can see, I will just quickly go through that, go back to the previous slide, that copper doped slide, quickly go back and come back. Okay, here you can see for the low copper content, the transition is relatively sharp. As you increase the copper content, slowly transition is broadened. Here you can see it is highly broadened. Ferromagnetic transition also broadened. So the TC also is broadened. You can see there will be a TC spread in the sample. So this will be actually related to the sample inhomogeneity. That is the most crucial factor. So we want to know whether the sample inhomogeneity will have any effect. Here we have used gadolinium as the example, and this also calculation part only. Here also I used a modified Ginsburg-Landau theory. People who know the Ginsburg-Landau theory know that generally people will take first two, the RHS, only two terms they will take. That means the linear part and the cubic part. And higher terms, higher M means normalized magnetization. But a higher order magnetization part people will not take generally. Generally, people will take only linear first time and second time. Here we have included third time also, m raised to 5 time. And first linear time also we have modified a little bit. Actually, this equation I got from another paper where they have shown that this modified Ginsburg-Landau equation, it gives a much accurate result for a material like gadolinium over a large temperature range. Actually, this Ginsburg-Landau or Landau formalism, it's a highly valid near the transition temperature, near the critical temperature TC. But this modified equation, it is valid over a large temperature range. That's why I used this. Actually, I missed the reference. Okay, I can share it. It is actually I missed that. Maybe in the next slide I will show. But there's a work in that cited work. My paper it is reference. This equation I got from another paper only. There they have described the derivation. Okay, here the different Gaussian distribution of the transition temperature considered. Generally, Gaussian distribution will be symmetric. That means around the mean point, it will be symmetric on both sides of the distribution, both sides of the transition temperature. But in the present work, we have considered skewed Gaussian. Generally, for real material, always you cannot ensure that your transition temperature inhomogeneity for material inhomogeneity parameter, you cannot predict that always there will be spread will be symmetrical. Uh, so it is more likely that transition temperature spread will be skewed. It is non symmetrical or asymmetric. See, for example, your material on making on magnetic material, say its transition temperature is 300. Uh, Symmetric Gaussian means it can go from, say, suppose it's a spread is 50 means transition temperature can go from 250 to 350. But in actual material, it is not the case. Suppose you are making the material with a transition temperature 300 means most of the time phase purity is 80% or 90% phase pure sample means most of the material transition temperature that distribution will be biased close to 300. Only a small fraction will be having variation around the 300. So I can say it will be spread will be around 250 to 310. If it is symmetric, it will be from 250 to 350 symmetric Gaussian. But skewed Gaussian means I can consider it will be say 250 to 310. That will be the most likely scenario for real material because see, purity will be always close to 90 or 95 or 99, something like that. So depending on the purity, most of the material transition temperature will be biased close to one single value. Most of the material will have one transition and the spread will be highly symmetric. So we have considered skewed Gaussian. See, many distributions considered. Some selected 1, 2, 3 are distributed. I have selected mean transition temperature 293 Kelvin, close to room temperature because that is the that is the transition temperature for gadolinium, experimentally observed gadolinium. So these 5 categories I have analyzed. You can see there is dependence with respect to distribution. Your delta H maximum is distributing. I'm busy in an online class. I'll call you later. Okay, sorry. Okay, sorry. Okay, so this is uh, okay. Okay, so the isothermal entropy change, it is highly dependent on the distribution. You see the curve, isothermal entropy is changing and your RCP also changing. See, RCP also changing. So from an isothermal entropy point of view, less distribution is better. Sorry. Hello? Hello? Okay, sorry, I will continue. Sorry. Okay, so the interesting thing is isothermal entropy and relative cooling power. The trend is different. See, relative cooling power, it is better for a sample having distribution. Sorry, okay, sorry. Okay, I think I lost. Okay, you can go through the graph. I got slightly disturbed. Isothermal entropy change and RCP both are affected by the distribution. Nature of the distribution also matters. That is the conclusion. Oh, sorry. Oh, okay, sorry. So, with this, I think I will wind up the present thing. So, since it is a technical task, I cannot go too much deep also. Okay, so with this, I will wind up. Okay, so these are the collaborators. Some of the collaborators contributed. And finally, I thank you all for the attending talk. Okay. Now we leave the session to the organizers. Okay. So please coordinate. Hello.
Yes, sir.
Okay. So I will wind up with this.
Sir. Okay, thank you so much, sir. And on behalf of Marthanam College of Engineering and Technology, I sincerely thank our resource person, Dr. Vinod K, for his valuable and insightful sessions today. And I also thank our respected management, principal, faculty members, and all the other participants for their support and active involvement. And a special thanks to the Atal Academy for giving us this opportunity. And thank you, everyone. And also, the feedback will be posted in the chat box, and everyone please fill your valuable feedback in that. And thank you all once again. And thank you especially for our research person.
I will call you later. I am in an online class. I will call you later. Maybe around 9 o'clock I will call. I am getting an online class. Okay, I will call you. Okay, so officially I can leave the thing now. I can leave.
Yeah, sir, sure.
Okay, thank you. I thank all. Okay, thank you.